Bismillahirrahmanirrahim. Assalamualaikum and very good day to you all. In today's video, we are going to talk about constructing the tip of gears. This video is a part of a four video topic on constructing the tip of gears. Okay, this is the third video on the topic. Okay, so this is from the chapter 13 from Shigley Mechanical Engineering Design book. Okay, so if you can see this portion, upper portion is the from the previous video. For the text from the previous video, it talking about the clearance. Okay, and referring to figure 1312 of the pinion is a center O1 is driver and turns counterclockwise. Okay, counterclockwise. The pressure or generating line is the same as the cord used in figure 13.7a to generate involute. Okay, there is a video on involute itself. You can see my previous video on involute, how to draw involute. And contact occurs along this line. The initial contact will take place when the flank of the driver comes into the contact of the tip of the driven tooth. This, it is better to have the nomenclature of the tip beside you. As I always remind in the previous video, this topic, while you are uh, trying to familiarize with the terms, it is better to have the nomenclature beside you when you are studying the book. Okay, because when I mention the flank, you can see the location of the flank right beside you. Okay, so so the flank is like the side of the tip. Okay, the contact another type of gear, another gear, upper gear, left gear, it will contact with the flank first. Okay, um, the driver comes in contact with the tip of the driven tooth. This occur at point A along in figure 13.12 where a random circle of the driven gear crosses the pressure line. Remember what is the location of addendum? Addendum, if you the tip of the gear, you divide with two parts, upper side and lower side, and divide them with half. Okay, the upper side is addendum, lower side is dedendum. Okay, if we now construct the tooth profile through point A and draw radial lines from intersection of this profile with the physical gear center, we obtain the angle of approach for each gear. We see in the angle of approach in the next slide. Here, okay. Here, figure 13.12, the tooth action. This is the angle of approach. This is the angle of approach. This is the angle of recess. This is the angle of approach. This is the angle of recess. You see here, this is gear 1 and gear 2. Gear 1 is the driver. Gear 2 is the driven. What is a driver? What is a driven? Driver also you can say is as a pinion is the same thing. Both are gear, but the driver is connected to the motor, and the motor move, give the force to the another gear. This is called the pinion. This is called the rack. Okay, but don't be confused. Both are gear. Okay, so this is the angle of approach when meaning that when the gear comes, okay, when gear approaching another gear, it is approach. When gear go out, it is recess. Okay, it's simple as that. Okay, have the nomenclature of the gear beside you and pair with this table so that you can understand more. uh, F the tip goes into the mesh like my hand here. I connect both together. This is a mesh. The point of contact will slide up to the side driving tooth so that the tip of the driver will be in contact just before contact ends. The final point of contact will therefore be where the addendum circle of the driver crosses the pressure line. Where is the pressure line? Okay, this is the pressure line. Uh, it is also called the line AB. You can see the word A, the word B here. This is for the line AB, meaning that both are connected together. Both are connected together. This connected together. It is a pressure line. This is point in figure 13.12. By drawing another set of two profiles to B, we obtain angle of recess for each gear in a manner similar to that of finding angle of approach. Sum of angle of approach and angle of recess for either gear is called the angle of action. Okay, line AB is called the line of action. So you can represent with your hand like I'm presenting here. Now, when I mesh both together, the line here, if you can imagine a line at your hand, it is the line of action, meaning both are working together. Okay, the same goes for the to the gear. Okay, rack with infinitely large diameter. We may imagine a rack as a spur gear having infinitely large pitch diameter. Okay, therefore the rack has infinite number of teeth. Okay, let me explain. Why does it represent a rack with infinitely large diameter? Okay, you can see any circle. Okay, let me take okay, this, let's say this is a circle. This is a circle. Okay, and this point of circle is this. You can imagine here. Okay, and you can see by physically it is a circle. Okay, how about what does it mean by infinitely large diameter? Meaning that it will become a straight line like this. Okay, now you see here you are sitting on the earth. Okay, and I want to make an analogy. You are sitting on the flat surface of the earth. Okay, of the earth. The earth is spherical. The earth itself is spherical, but you cannot see the spherical unless you are high up in the sky, high up in the tower, in the tall building. You can see the curve. You can see the curve. But when you are sitting on the earth, on the soil, on the ground, you will find the ground is flat. Okay, okay, but you remember the earth is circle. Okay, the earth is spherical. Okay, it is not a flat, it is a spherical. Okay, when you are sitting on the earth, you on the ground, you are sitting on the ground, you will see it is a flat like this. Okay, so imagine a rack. Okay, we get after this, we in the next video, in the next slide, you can see the rack. Okay, imagine a rack with a large diameter, meaning that it is becoming flat like this. It is becoming flat like this. This is flat. Okay, uh, this is what means by infinitely large diameter. When the rack has infinite number of teeth and base circle with infinite distance on each point, the side of involute teeth are on a crack are straight lines, making an angle of the line equal to the pressure angle. Okay, this figure 1313 shows involute rack with mesh with a pinion. Okay, let's and base pitch is related to circular pitch by equation PB equals to PC cos theta, which is base pitch equal to center pitch cos theta. Okay, you can see here. This is the pitch. This is the rack. With or both have teeth. This have teeth. This also have teeth. Okay, so uh, remember this the gear is outside gear. Okay, now what happen if the gear is inside gear? The pinion is matched with internal gear. Okay, there are both kind of gear. To a kind of gear, the gear that is outside and the gear is internal gear inside. Okay, figure 1314 shows an pinion with mesh with internal ring or gear. Note that both of gears now have their center of rotation on the same side of the pitch point. This position on the addendum circle with respect to the pitch circle are reversed, and the addendum circle of the inner gear lies beside the pitch circle. Note 2 from figure 1314, the base circle of internal gear lies inside the pitch circle near the addendum circle. You can see here. Yeah, this is internal gear. If you can pause the video, go back to the video on the rack, on the infinite rack. It is an outside gear. Now, representing the inside internal gear. Okay, this is the pitch circle. This is the pressure line. See here the pressure line. The same concept. If you can see the figure 1312 is the same concept. The pressure line. the line AB, that line, okay? And the addendum circle, and you can see the base circle, P circle, and everything. Okay. Another interesting observation concerns for the fact that the operating diameters of pitch circle or a pair of machine gears need not be the same as respective design pitch diameter of the gear, though this is the way it has been represented in figure 1312. If we increase the center distance, we create two new operating pitch circle having larger diameter because they must be tangent to each other at the pitch point. Thus, the pitch circle of gears really do not come with existence until a pair of gears are brought into mesh. Okay, so we can see this picture. Uh, okay, changing the center distance. Okay, changing the center distance has no effect on the base circle. You, if you have, you can pause the video, go back uh, to the previous slide showing where is the location of the base circle. Uh, it is because they are used to generate two profile. Thus, the base circle is basic to the gear. Increasing the center distance increases the pressure angle and decreases the length of action. We will talk about pressure angle in the other videos. There is other video specific on the pressure angle itself, and decrease the length of action, but the teeth are still conjugate. Requirement for uniform motion transmission is still satisfied, and angular velocity has not changed. Okay, so that's all for part 3 of the video. We continue on the last video for chapter 13.5, which is we are going to do example. Okay, so thank you very much.